take a look at some thermochemistry and electrochemistry. Got an exam coming up, so let's review this stuff. It shouldn't be too bad. It's pretty easy. We basically have things like endothermic and exothermic reactions. You kind of already know the endothermic is where the heat is going to be on the left side. We got reactants, and where the exothermic has the heat on the right side as the products. So you can see when we get positive for the endothermic, negative for the exothermic, and well, we have to calculate this thing. We call it enthalpy. That's the heat that's sort of released or absorbed in the reaction. So here's some state changes, and as we go through different states, it requires a different amount of H. So you have a type of H that goes through here, another one that goes through here, another one here, and then each one of these have different H steps. Usually, the enthalpy is going to be for when we actually move through temperatures, and the latent heat should be when we go through the process here. But anyway, so we have these different processes, vaporizing, melting, fusion, sublimation, condensation, and we should probably figure out which one is which. So I made this little list right here, so you can see basically if we melt stuff, like so for example, ice into water over here, it's an endothermic process, so it requires the heat to go into the ice on the left side, and then the water becomes melted on the right. Um, you can think about the entropy of this system, because this is kind of the next important part, is the entropy. So we have enthalpy, which is the heat in and out, and then the entropy. Well, so the entropy is kind of just like maybe I like to think of it as order, but we could also think of it as motion. So order and motion. Um, and the idea is that, um, so here, if we have the ice, it's kind of stuck. It's like a crystal form. And so the motion is very restricted, and it's also very patterned, so it's very organized. And then as it melts, then the water becomes very disorganized because it's just kind of particles flying everywhere, and it has a lot of motion. So, so that's basically the entropy that is um, may have switch speeds. Got to make sure that this is actually correct. And yeah, let me double check this because this is supposed to be. Oh, this is the surroundings. Right. So the entropy of the system increases, right? Entropy of the system. So this is the entropy of the system right here, and so that's why that's in the line here. But the entropy of the surroundings decreases because you have to have a kind of equal balance, right? If the entropy of the universe to be zero, then you'd have to have positive on the system and negative of the surroundings. Now for the exothermic, you kind of see that the water here becomes ice, so it's a reverse process. Seems a little weird that freezing is an exothermic process, just like burning, but that's kind of the way it is. And just it's all the reverse. So we kind of think of this entropy and the enthalpy and their combination, and then we have to think about the Gibbs. The Gibbs is the energy that's given out. So we have three different types of things that are sort of given out or absorbed during the reactions. We have the energy, we have the heat, and then we have the entropy. And those three are related by this little equation right here. This is the Gibbs-Helmholtz equation right here. So I didn't write that, but it's the Gibbs-Helmholtz. Um, and this is also related to the KEQ, the constant for the equivalence constant for a reaction. That's pretty cool. So then we can sort of put this equation together and stuff. And this is for standard conditions, okay? So that means 1 mole, 1 atm, Q equals 1, which is not AEQ, which means that it's not at equilibrium, right? And 298 degrees Kelvin. We can also consider how we can solve for a change of a reaction. Usually requires the products times their coefficients. and then we subtract the stuff from the reactants. Right? So it's the products minus the reactants gives us the formation, which can usually be energy or entropy or enthalpy, whichever one you want to use here, but this is kind of the general formula. This is how you kind of, anytime you're forming something, you kind of use this formula. And these are usually things that you'd have to look up in a table. So here's an example. We have these G's here, the Gibbs of formation for water. We got like negative 236. I think this is kilojoules per mole. About to add the units here. Kilojoules per mole. Let me just put it in one spot, kilojoules per mole. And we'll just have to go with that. For the other three, it's getting a little bit small. Okay, and so now we kind of have how we can solve for these types of things. Now, if we're not at the standard conditions, we have to consider delta G plus RTLNQ, which again kind of leads us to this whole situation. But this is for G equals 0 at the EQ, where Q equals KEQ. Yeah, so this might seem a little contradictory, so I'll just have to do research on that again. Some of these things are a little bit confusing as usual. Let's look on the left over here, how we have this energy that we have to, the barrier here. Consider the enthalpy. Um, this change of energy is the internal energy. And then if we add the PV, or the work volume, um, pressure work volume stuff, then we get enthalpy. Enthalpy is also the number of bonds broken minus the number of bonds formed. So there's different types of ways to think about enthalpy, not just heat. I guess heat is more like Q, although remember back in this equation here, Q is essentially equal to enthalpy times the mole. So it's kind of like the same thing. Um, and when I say Q, there's actually three types of Qs. We have Q being the charge, for example, in the next stuff, but charge is for electrochemistry. It's like kind of that stuff, the charges. Then we have Q being heat, and then we also have Q being the equivalence quotient ratio stuff. So Q is popping up everywhere, and that's kind of annoying, but that's why I try to color code these. For example, this is the delta S of the system, or is it of the universe? I think it's delta S of the universe. But anyway, let's look at this stuff because we should know what a spontaneous process is. Spontaneous process is the idea that it occurs naturally. So you have negative Gibbs, you have positive entropy, uh, and if we're at 0, we have equilibrium. We get this equation here. And if it's positive Gibbs, then it required work input. Okay, so this is kind of about the Gibbs stuff. Um, Kind of relates to electrochemistry a little bit because here we have the Nernst equation. If we're calculating non-standard stuff, to consider all this stuff again, we have like the Q, reaction quotient, RT, and F. F is Faraday's constant, and we got these moles, and we have Gibbs showing up again. But what is this electropotential? The electropotential is this. So it's kind of like, what's the natural voltage of stuff? And usually if stuff is positive voltage, then current flows. So it's going to be spontaneous, and so it runs. So positive E cell is going to be spontaneous, and the negative Gibbs. Those two come hand in hand. As the E cell increases, the Gibbs decreases. So we're kind of changing chemical energy to electrical energy with this cell right here. So we take the cathode. And the cathode and the anode. We should take a quick moment to review oxidation and reduction, right? Because all this has to do with oxidation and reduction. So let's go over to Q over here, so charges and stuff. Oxidation and reduction. Um, so here's a simple equation. Notice that this compound here is neutral, and then we have three O's. O's usually take -2. So -2 times 3 is -6. So O has a -6. And I think this is supposed to be -2. Sorry. Quick little typo. Yeah. So -2 is for the O's. They become the -6 because there's three of them here. Here there's only one. Here there's two of them, so it becomes -4. These compounds are all neutral, so we have sort of a 0 on the outside. So is that one. If we look at Fe over here, consider if this is a neutral compound, then we have to equal it out. This has to be +6 over here. This is necessary. And so then these must be +3. Over here, this is a 3 times whatever's in here. Okay, so what's inside is we have -2, and then we have a +2, which makes this 0. Multiply that by 3, and you'll get the stuff up there. So all these numbers have to kind of add up. And over here, again, we kind of have 4, because this is -4, and there's 3 of them. And so this is ultimately becomes -12. 3 times -4 becomes -12. Okay, so we're kind of balancing it all out here. Um, so let's see. This is the important process here is to realize that if we're oxidizing, then we're losing electrons. So the electrons actually go on the right side. How many electrons did we lose here? I think we needed 2 electrons because 4 minus 2 gives us 2. And over here, on this side, we have gained electrons. So electrons go on the reactant side. I'll put it right here. Plus, we needed 6 electrons. And that's why we had to multiply this thing by 3 so that we can get 6 electrons on this side, and then 6 electrons on this side. And so, yeah, so we kind of have to balance all that stuff out. So the idea here is to split these up into 2 different equations. We got sort of the oxidation equation here with CO. Scoot up a little bit so you can see we're just pulling out CO and CO2 to these things into one equation, and then we have this equation pulled out over here. So that way we split them. Now we're going to balance them. Usually we kind of have to, if there's a bunch of O's, we add H's. We can put H2O's on the other side. This makes conditions are acidic in this case because we have a bunch of H pluses lingering around. At that point, we tend to want to balance the electrons, multiply them by coefficients to cancel them out, and then we kind of have the complete reaction here. If we want to transform into basic situation, then we have to add OHs back in. So this is the process for oxidation and reduction reaction. Let's go ahead and return here. These are just some of the rules. This is how water does it. And now we have the voltaic cell again. So now we've sort of realized, okay, so the cathode is the thing that is reduced. So it gains electrons, meaning the electrons are on the product side. So it's over here. This is the cathode. I'll show it now. So this is the cathode. But no. Oxidation number goes down because it gains electron. I think I put these backwards. The reactants go to the cathode. Hopefully this is correct. Just gotta always double check this stuff. If it gains electrons, then it has to be on the reactant side. If it loses uh, electrons, then it has to be on the product side because they're coming out. So here they're going in, here they're coming out. As you can see, we have the arrow here that traces where the electrons are going from the right side to the left side. You get that positive voltage there. So they're popping out of this reducing agent, and they are appearing over here in this oxidizing agent. All right, so we have the salt bridge between them, where ions are sort of popping out back and forth. Positives go on this side, negatives on that side, and realize that salts must be pretty soluble. So we like Na, we like K, and here we like NO3. Here comes the we have the voltaic cell, which is volts. Oh, sorry, positive volts makes it spontaneous. The electrolytic cell is non-spontaneous, so it's negative volts. All right, it's actually backwards. So you have to apply voltage to get the electrolytic cell to work. And so the electrolytic cell converts electrical energy to chemical energy. It's just backwards. All right, we have a concentration cell here where we set the voltage is equal to 0 because it's the same substance. But the electrons, I don't know whether electrons flow. I'm not exactly sure what's going on with this because if the electrons were to flow, we would have voltage. But I'm going to go ahead. I didn't really go too far into this concentration cell stuff, but just realize that E equals 0 because it's the same substance there. So yeah, we get the mole of electrons sometimes are in these equations, and all we want to do is multiply that maybe by F, and we'll get the number of coulombs. Um, yeah, so this is pretty quick review. This is essentially almost everything we needed to know for our chapter, for our exam here. So that's pretty fun. Just a bunch of stuff to kind of know about thermochemistry and electrochemistry. Shouldn't be too difficult. Um, and yeah, awesome. All right, thank you so much.